Welcome to the demonstration corner. Today we'll be talking about the next generation of the one-dimensional testing module for the transient plane source. We'll be doing a demonstration on our MP-1, which combines transient plane source, transient hot wire across quite a few technical advantages, which make this the leading transient method on the market. So over at this table, we're going to talk a little bit about what is traditional one-dimensional module, and then what have we done to really help the one-dimensional module jump ahead and it be a much easier and more complete measurement. So typically for one-dimensional module, what we're doing is trying to match the dimensions of the diameter to, and it's usually a circular with the dimensions of a center. Now, it is the one-dimensional module described by the ISO 22007-2. It's described for elongated materials. So materials that are taller than they are diameter or radially large. So we try to do our best fit to find a diameter that fits very close, diameter of sensor that fits very close to the diameter of sample. Now, typically, when you're measuring a sample for thermal conductivity and thermal diffusivity along the length of a rod using the one-dimensional module, you would input the volumetric specific heat. Now, there is a module for the transient plane source available on the MP-1 for measuring direct specific heat. You would measure that as step one, or if you know specific heat by rule of mixtures or DSC, and you would input that and measure along the length with that input, you would get thermal conductivity and thermal diffusivity. So possible, but we've taken a major jump forward with our proprietary calculation, which allows us to take that same aluminum material, whether it's a height of something like that, whatever the sample is in a one-dimensional shape, elongate it, by putting a backing material or an insulation on top of the sample and inputting the thickness of the sample into the software, we have now a dimension. Because now we have a dimension, and using the boundary effects, the heat penetrates through the material, hits the boundary, and we have a defined dimension. We can measure directly the thermal diffusivity. So we know the thermal conductivity and thermal diffusivity and the output of specific heat. So no longer do we need to input the specific heat, even better, with one measurement with this module now that's called one-dimensional slab or 1D slab. You get thermal conductivity, thermal diffusivity, and specific heat. So you don't have to do a secondary measurement first. You just measure directly. There are other advantages to that. One is now that we have boundary effects, we input the thickness, we can measure materials of higher conductivity or even lower conductivity at a much smaller height. So this is an example of a one-dimensional sample. This is 21 millimeters in diameter, which matches just slightly larger than our 20 millimeter sensor. This is about 10 millimeters tall, I believe. 5 millimeters tall, sorry. From that, we'll show you some data from that, we get thermal conductivity, thermal diffusivity, and specific heat. So that would typically be a relatively difficult sample to measure with just one-dimensional because we'd be trying to keep the heat within the boundaries. Well, when you insulate it and you create a slab out of that, we know the boundary. We can measure that as part of our, when we make a measurement, we know the input. Rather, you input the thickness, and now we have a dimension. So we get all three properties. So it allows us a great deal more flexibility on sample height, and another big advantage is you don't need the input. So it's really a wonderful next step, next generation on the one-dimensional module. So we're going to show physical setup, then go to the software, and show you some data. So I'm just grabbing the pieces here. So we've got a specific set of sensors designed for the use on 1D slab. So again, if you acquire the 1D slab module on the MP-1, if you acquire the one-dimensional module, you get the 1D slab as part of that same package. So you can run the sample according to the ISO 22007-2, or you can run it with this new upgrade, which is 1D slab. So you get both of them when you purchase the 1D module. Because they're so closely related with the advantages of both, I think it's important to keep them together. So our sandwich would be, if we run this symmetric, and again, you can run this asymmetric or single-sided, where we're going to do symmetric, the bottom part is insulation and sample. Now you would, of course, measured the thickness of your sample. We've already done that. And then we would do a mirror on top. And you would do your best to line up the sample with the height, rather the diameter of the sensor. And completing my thought on the sensors, we have a range of sensors with no extra Kapton that are precisely the diameter of the double spiral that's encapsulated. So this is a 20 millimeter diameter sensor, and with no extra Kapton, you can line up the stack directly to the spiral. So you have no heat loss with extra Kapton. Everything is a one-dimensional shape. So that's a symmetric setup. If we were going to run that asymmetric, we would just have the insulation as the bottom half or the top half, and then we would have our sample and then insulation. So that's our setup. So we're going to go to the software now. Here we've selected our 1D testing module with the symmetric and slab configuration. This is our controller, and we're using the room temperature sample holder that's plugged into the front of the instrument on port 1. The sample is aluminum. It's 12 millimeters tall. The area is 346 millimeters square. The sensor we already inserted the sensor. There's plenty of demo videos if you want to see the sensor, how that connects to the adapter. You can peruse through our demo videos and see that. The temperature is automatically taken from the adapter. So whether you're doing this on the bench, it records the temperature of the bench, or if you have that in the chamber, or if you were using the temperature platform to run the same sample with temperature, it would record that. And now we can go to run a schedule, because that confirmed the sensor is connected properly. So we're going to run a 2-second test at 3,000 milliwatts. That's just, again, to generate enough heat. This is a relatively conductive material, around 180 or 190 watts per Kelvin. So in this schedule, we'll run 5 measurements with a 10-minute delay, 2 seconds test time, and 3,000 milliwatts. We'll start that. So we're not going to wait for that to run, but this is your data acquisition software that is the location of the schedule. And if you wanted to run more samples on one of the other channels, of course, you can go in and do another schedule. So we've separated the software into 2 applications. One is data acquisition. So here we can run a single channel or multiple channel with different temperatures as well as different methods. And then we'll switch to our analysis, or a transient analysis application, where we pull up data and we can analyze that data for thermophysical properties. So here is that brass, the same ones that I showed you earlier that are 5 millimeters thick. Again, no input of specific heat. These are all measured properties: thermal conductivity, thermal diffusivity, thermal effusivity, and volumetric specific heat. Those line up well with expected values for yellow brass. Excuse me. Here we have stainless steel, and these were 3 millimeters tall, 20 millimeters in diameter, 21 millimeters in diameter. Thermal conductivity, thermal diffusivity, thermal effusivity, volumetric specific heat. Again, no input. Those are all measured. Just giving you some examples of materials that we've measured. Here is the aluminum at 10 millimeters, roughly 10 millimeters. Thermal conductivity, thermal diffusivity, thermal effusivity, and volumetric specific heat. Now, this aluminum is 6061. That thermal conductivity is a little higher than what you'll see for a bulk property. This is an extruded aluminum, so you get some anisotropy in the direction of extrusion. We see that in slabs as well. This is one-dimensional shape, so it's a rod that's extruded. So you get alignment, and you get slightly higher conductivity because of that. If this was a sheet, you can also see the same thing. So if this was a bulk sample, like a block, and it was cast, formed, the values would be in the 170s range. Because it's extruded, you have a slightly higher value. So those are 3 examples of materials. The conductivity range of this 1D slab is roughly polymers up to very high conductivity materials with the advantage of being able to test thinner format. So we're really excited to be able to bring this proprietary capability to the market. If you have any questions, let us know. We're happy to demo this or share it with you. We have application sheets. And thank you very much for your time.